To measure a compacted clay's response to wetting after it's been compacted, we're going to do sort of the inverse of a consolidation test. Instead of taking our odometer ring and carefully trimming an undisturbed soil specimen to fit inside it and run a consolidation test, instead we're going to compact the bulk soil mixed to a particular water content that we're interested in to a certain target dry density, hopefully, and then we're going to run sort of the inverse of a consolidation test by placing it in a basin with a large porous stone on the bottom. We have a top porous stone which is just the right size to fit inside the ring, and once that system is there, we can place that basin over on a loading system, apply a moderate load, and then flood the sample with water. And when the water has access, when the soil specimen has access to water like that, if it's been compacted to a high density, it's going to have a tendency to soak in a lot of water, to swell vertically upward, right? So we're going to track that at first a moderate load, and then we're going to halve the load and see how much more it swells, halve the load again, etc. We're not really interested in the time curves per se, more just the final amount of swell we get at different stress levels for a particular single compaction condition, right? I'm going to compact this specimen to some dry density with soil at some water content. So in order to do that, we need to know about the ring, of course. We want to make sure we have a mass and a diameter. We're going to compact it on a kind of specialized base plate here that has a little step in it. That step is going to leave a hollow space at one edge of the ring because we want to start this test with the stone down a little bit inside the ring so there's room for it to swell without spilling out the sides of the ring. So we also want to measure the height with the calipers down to that step. We can use the step function on the calipers for that. Make sure we have a good zero, and then we drop this vertically, and it's telling us it's 22.48 millimeters. So that's the height that our specimen is going to be, because we're going to trim it to be flush . Getting slightly different answers here. I'm going to double check. More like 22.25. So that's going to be the height of our specimen, 2.25 centimeters. Then we have a decision about how to compact it. There's no particular standard way to do this. This is not an ASTM test per se. But if we want to mimic the density that we had for the compacted clay triaxial tests, that wasn't particularly dense. So we probably don't want to use the very large modified Proctor hammer and pound on it too hard. We're going to get way too high of a density. So we'll use the smaller standard Proctor hammer. And we also have to remember that instead of a 4.5 inch high compaction mold, our specimen's only an inch tall. So we need to sort of proportionally scale down the number of drops that we do so that we get something like the energy that will give us about the target density that we want. I'm also putting a little filter paper in at the bottom. We don't want to compact the soil and have it stick to the mold, and when we take it apart we see big chunks left out of our specimen. Certainly not good. So we'll finish assembling the mold. We're going to choose this hammer. We're going to do the compaction on the floor because dropping compaction hammers on wooden furniture, not a good idea. And then we'll trim it up and be ready to load it. So to compact our bay mud specimen for the swell test, we're going to use sort of a hybrid procedure. We're going to compact it in two thinner layers than we would normally have for a compaction mold, but we're going to apply less drops per layer also. So we're going to put in a scoop of soil, Again, this is pre-conditioned to the same moisture content that we used for the triaxial strength tests on compacted clay. And zip that up so it doesn't dry out. And we're going to apply 15 drops of the small standard Proctor hammer. So it has a lighter mass and a smaller fall height than the modern test would have. And again, the Proctor hammer has a diameter that's half the diameter of our specimen. So we're just going to go around the outside and not waste any of our drops in the middle. When we use a hammer, we want to use it just like we would for a compaction test. So make sure the hammer is vertical and you get the full fall height for every tamp. Okay, and that's a pretty thin layer, so when we compact the next layer, we'll also still be compacting this material a bit too. So now that the soil is compacted, we're going to come along with this strange looking implement, which is designed to cut away the soil from the collar right around the edge so that we get a good clean removal of the collar and don't break away a lot of soil at the top surface either. Turn that until it's all the way down in contact. Great. And then we're going to trim it down with the steel blade that we've used for many of the labs. And again, this is going to be a consistency more like shaving away chocolate than it is like the gooey natural material that's up at 90% water content or whatever it is that you would be testing in an undisturbed state. So here comes the collar. Well, that's on there pretty good. There we go. And here's our blade. I'm going to trim this just flush with the surface of the ring. I'm going to try to not take out big chunks, so I'm trying to slice as much as I can. I don't want to pull it in tension. I want to give it the excuse to break out a big chunk. Of course, on the other side, on the bottom side, we have the step and the filter paper, so we're not going to be trimming the opposite side at all. But we do want to get all the way down till we can't remove any more soil, because that's the volume that we measured. And so when we measure the mass of the soil plus the ring, we want to be sure that that's not including extra soil that's up above the surface here. So you can see that this flakes off shavings. It's important that I keep the blade across both sides here of the ring, right? I don't want the end of the blade gouged down inside. It's looking very good. All right. So, the only thing we weighed earlier was the ring itself, so we definitely want to take it off the base plate. And that should be an easy step. Here we are. There's the filter paper. You can pull the filter paper off, measure the weight of the moist soil and the ring, and subtract to get the soil mass. Then we'll assemble it in this basin and set it up on the load frame and apply the seating load. So here's how we assemble the specimen with the other pieces in the sandwich. The side we just trimmed is the bottom surface. So we're going to place that down directly against the larger bottom porous stone. Then comes the porous stone that fits just within the ring. And again, it's seated down now where that step was in the mold, so there's some room for the soil to swell vertically without spilling out of the mold. Then we're going to add this brass disc, which basically is there to help distribute the stress, because we're going to be applying the stress to metal yoke here. We're going to actually have the dial gauge. It's going to be a dial gauge instead of an LVDT, and that's through the hole in the brass disc. So theoretically we're right there in the center of the top of the porous stone. Can make a couple of small adjustments there. Great. Maybe one more back a little bit. That's the wrong screw. There we go. We want to make sure we start the dial gauge in a position where there's plenty of room for it to expand vertically. And then we can put this loading yoke over the top of it. We'll carry the whole system over to the same frames where we did the UU test with the hanging weights. That's where we're going to run this. We only need a place to apply some dead loads and keep them constant, so we don't really need a computer for that. So we'll set it up and start taking some data. So we've got the system in the loading frame, and the first thing we're going to do is put a weight of 4 kilograms on there, which is pretty large compared to the strength testing we were doing before. But the area of the sample is about 80 square centimeters. So 4 kilograms is a relatively small stress. That's our seating load. So we're putting it on there. We're looking at that dial gauge reading now that we're seeing as indicative of the height of the specimen as it was compacted. So we have that measurement of the mold minus the step for our specimen height, and we're associating that height with this dial gauge reading. All the subsequent dial gauge readings then are interpreted relative to this value, which is 4.62 millimeters, and changes from that will indicate changes in the specimen height. Now that we have this value, we're going to go to the maximum stress. Before we wet it, we're going to put on 40 kilograms, 10 times this amount, which will represent about a half an atmosphere of stress. 40 kilograms over 80 square centimeters is about 0.5 kilograms per square centimeter, which is about 0.5 atmospheres, or 50 kPa. So in going from 4 kilograms to 40 kilograms, the specimen got a little bit shorter, 4.62 to 4.45, but not too much. It's pretty stiff, and of course it's confined radially. But that's our initial value now from which we're going to calculate the swelling, the 4.45. And we're going to flood it with water and not change the load at all. So this first increment is really not an unloading as much as it is just the wetting. So we're pouring water around the outside. That's going to flood the bottom porous stone. There's no filter paper left at either of the interfaces. I'm going to give it just a second there to let some air out of the top if it wants to do that before I completely submerge it. And now we expect it to change direction. We expect as it soaks water in now, the needle's going to reverse direction and it's going to head higher. The sample's going to get taller. But that will take maybe a day and a half or something like that. Especially this first increment where there's a lot of air in the voids. We'll just have to come back and see. So we're not trying to get a time curve. Oh, it looks like we have a little bit of hydrocompression. That's interesting. It's gotten slightly shorter as I wet it initially. That won't last. But in a couple of days, then the first increment will be over. This first swelling, we'll write down how much taller it is, and then we'll take off half the load, which will reduce the stress by a half. will drop from 40 kilograms to 20 kilograms, and we'll let it equilibrate again, and we'll see how much more it swells all the way down to 10 or 5 kilograms. And then we can construct a curve to see how much percent swell we would expect depending on how much overburden stress is on the soil. Again, compacted to this one point in compaction space, right? This is some particular compaction water content and dry density. And so all of the subsequent swell data applies to that one location in compaction space.